Infinity has some weird properties. If you add anything to infinity, it's infinity. Subtract anything from infinity, and it's still infinity. Multiply anything by infinity, and guess what? You get infinity. Divide infinity by almost any number, and you'll get infinity. We'll get back to why that's the case later. Infinity is kind of like an all-devouring number, eating almost everything that comes its way. But would you believe me if I told you that some infinities are bigger than others? There are two types of infinities, countable infinities and uncountable infinities. Let's take the set of all natural numbers. That's 1, 2, 3, 4, 5, and so on. Is that countable or uncountable? We can easily find out by using what's called an one-to-one correspondence. A one-to-one correspondence takes the numbers of one set and matches it up with another. Let's say 2, 4, 6, 8, 10, and so on. We can match the numbers from this set to this set like this. If these sets stretch to infinity, which they do, no number will be left unmatched. Every single number will have a corresponding pair. These infinities are the same and are countable. Keep in mind that both these sets have a definable pattern. What about integers? Easy. We have this set of integers 0, 1, -1, 2, -2, 3, -3, and so on. And then we have this set 1, 2, 3, 4, 5, 6, 7. This pattern can go on forever. No numbers are left unmatched, and there's a definable pattern. We have a one-to-one correspondence. These infinities are also the same. All rational numbers? Here we run into a bit of a problem because of the fact that there can be an infinite amount of possible numerators and an infinite amount of possible denominators. Well, all rational numbers can be written in a square format like this. You might be thinking, there's no way we can hit all of these and have an identifiable pattern. Well, there's actually quite an easy way. If we draw a zigzag line through this formation, we can get this. Now, if we ignore the pattern and just list off the matched numbers, 1 to 0, 2 to 1 over 1, 3 to 2 over 1, 4 to 1 over 2, 5 to 1 over 3, 6 to 2 over 2, and 7 to 3 over 1, it appears that there is no real pattern. But then it becomes clear if you arrange it into a box formation. No numbers left unmatched, this pattern can continue forever, and so those infinities are the same as well. One more level, the real numbers, all natural, whole, rational, and irrational numbers. How are we meant to possibly arrange all these numbers into one identifiable, infinite, matching series? The simple answer is, we can't. Say we have this series of real numbers. And you say, oh, okay, we've hit every single real number possible, and it's on a list. But wait, we can always make more. Say we circle the first decimal place of this number, the second decimal place of that number, the third decimal place of the third, and so on. Now we have a new decimal number. We don't have this on the list, so let's add it. Oh, but wait, we can do it again, except with the second decimal place of the first number, the third decimal place of the second number, and so on. Add that to the list, because we have a new number. And we can do it again, and again, and again, and again, and again. And therein lies the problem. No matter how sure we are that we have hit every single real number, there's always one number that we've missed. If we're sure that number was the last one, there's always more, and another, and another, and another, and another, and another, and another. The set of real numbers isn't just infinite, it's uncountably infinite. Infinity has been shrouded in mystery since its philosophical discovery in the 3rd century BC in early India. Many paradoxes, theoretical problems, and more have spawned since its mathematical acceptance. Take, for instance, fractals. Fractals are a type of mathematical image that repeats itself on every level. This is the Koch Snowflake. The Koch Snowflake has a finite area, yet an infinite perimeter, which, if you think about it, should not be possible. If we have 0.99999 recurring, infinite nines, then it would equal 1. We can show it like this. Here's another hypothetical situation. You place an infinite number of monkeys in a room with an infinite number of typewriters. The monkeys hit keys at random on the typewriters for an infinite amount of time. If this goes on forever, there's a 100% chance that at least one of the monkeys will produce one of Shakespeare's plays. Think about it. Each key has an equal chance of being pressed by the monkey. That's a 1 out of 47 chance of a single key being pressed by one monkey. Say the final result that we wanted was Romeo and Juliet. The number of characters in that play is roughly 145,000 characters. The probability of any key being pressed at random to produce Romeo and Juliet is 1 out of 47 to the power of 145,000. Now that's an infinitesimally small number, 6.46 to the power of 10. No, 6.46 times 10 to the power of negative 242,455. With a limited amount of time, this feat would be almost impossible. However, we have infinite time, therefore you can try every single combination of any keystroke ever and still have time left over. So there's a 100% chance that one monkey will end up producing a masterpiece.